KD trees, the data structure for spatial search in multi-dimensional spaces. Essentially, it's a binary search tree that organizes points in k dimensions by splitting the space one dimension at a time. Each level of the tree alternates the splitting dimension, allowing us to efficiently search, insert, and perform range queries across large point sets. They power many real-world systems, from geospatial map apps like finding the nearest coffee shop, to nearest neighbor searches in recommendation engines, to range queries when all points within a certain radius are needed, to clustering and grouping for data analysis in machine learning. With KD trees, spatial queries can be scaled to millions of points. Each node of a KD tree stores a single point. The tree alternates splitting dimensions at each depth. Let's see how the splitting axis cycles in 2 dimensions, when k equals 2. At depth 0, split on the x-axis. At depth 1, split on the y-axis. At depth 2, back to the x-axis. At depth 3, back to the y-axis. And so on. This alternating ensures that neither dimension is favoured, keeping the tree balanced in both x and y directions. For 3-dimensional data, the cycle is depth 0, x-axis, depth 1, y-axis, depth 2, z-axis, depth 3, back to x, then y, then z. This pattern generalizes to any k. Simply take depth modulo k to pick the axis. Now, let's walk through inserting 6 2D points. First, we insert 30, 40. At depth 0, we split on x, but since the tree is empty, this becomes the root. Next, we insert 5, 25. At depth 1, we split on y, compare 25 to the root's 40, and go left, with 70, 70. We split on y again, compare 70 to 40, and go right. Inserting 10, 12. At depth 2 means we split on x. We compare 10 to 30 from the root, go left 2, 5, 25. Then compare 10 to 5. At depth 3 we'd split on y, so we go right of 5.25. Fifth, 50, 30 at depth. 2. Split on x, compare to 30, go right to 70, 70, compare 50 to 70 and go left. Finally, 35.45 at depth 3 splits on y. Compare 45 to 30 at node 50.30 and go left. When searching for the nearest neighbor, we first recursively traverse down, always following the side of the split that contains the query. Next, keep track of the best distance found. Finally, upon reaching a leaf, backtrack and search any sibling region that could contain a closer point. This pruning drastically outpaces brute force search. On average, insertions and searches run in O log n time, though in the worst case, meaning highly unbalanced data, they can degrade to O(n). Nearest neighbor queries also average O log n, but again can be O(n) in the worst case. Space usage is linear in all cases. KD trees excel for 2D or 3D spatial data and fast proximity lookups. Think mapping apps or clustering. However, as you add dimensions, the volume of space increases so fast that data points become sparse. Distances between points converge, making nearest neighbor distinctions less meaningful, and the tree requires frequent rebalancing to maintain performance. In those cases, KD trees perform poorly. To wrap up, KD trees balance structure and speed for spatial data. They're ideal for mobile and geospatial use. Think maps, augmented reality, or games, so mastering them gives you an edge in any system needing fast, multi-dimensional point queries. Time to code. In this quick walkthrough, we'll see how a KD tree can be applied to a simple mobile app. TutorialApp.Swift launches the app, sets up the main window, and shows the content view. This app, coded in Swift, follows a clean MVVM design. That's short for Model View View Model. Tree.Swift contains the model. It defines our KD tree for 2D points. The node class stores a point and optional child links. The tree class handles inserting new points and checking if a point exists. ViewModel.Swift connects the tree model to the front-end interface. It keeps track of tap points, user input, and search results. When the user adds a point, it normalizes and rounds the coordinates, then inserts them into the tree. When the user searches, it passes the input and checks the tree for a match. ContentView.Swift is what the user sees and touches. Let's tap anywhere on the screen of this real iPhone 16 Pro Max to add a point. Each point is shown with a white circle and its normalized coordinates. At the bottom, there's a search bar where you can type a point and see if it's in the tree. And that's it. Thanks for watching. Now go try it out yourself in your preferred programming language.